right. I have sound on. Cool. Very good. And then you know where to see these videos if for any reason you want to see the videos back. Presumably you found this website by now pretty well. And then they're all just right here. I think I don't have them under that yet because I haven't added them to the playlist. But I will soon.
What about the copyright strike?
So I sent in an appeal for that. I'm supposed to be able to use that stuff for educational purposes. I think they don't know it's an educational channel, so I told them. And maybe it's not officially an educational channel, but the other stuff is still up. The copyright strike was only on the aims of education thing, but you see, these are all here. So that's yesterday. We're missing an hour, right? That's roughly 3 plus 3.5 hours, and we did 8. And then today we're live. So. Should be fine. Send me a message if you can't find anything, and you can also watch Professor Sipser's lectures if you prefer those. You'll have to actually, if you do end up watching them, let me know what you like about the two of us. But okay. All right, everything's working, very good. Okay. So we'll begin today with, is that okay for you?
Yeah.
That's probably actually easier to see than yesterday, huh? Okay. So I began with a review slide, and I just put all the theorems in here from yesterday, and this was set to tentatively be the first hour or not, depending on how much time you want to spend on this. So just let me know how you're feeling or what you're doing with these. But okay. So the first thing we talked about yesterday, and then we got in trouble for it because Google was listening, was we listened to the talk by Amber Huffman, and you set some goals for master's level computer science education. My big takeaways from that, oftentimes I think at the master's level of education, students are expected to be, or not students, professionals once they're graduated, right, are expected to be sort of opinionated on some matters, right? So like, you should have an opinion on open source software. You should have an opinion on open source hardware. You probably should have heard of RISC-V, even if you don't know what it is, right? My hope is that by sort of exposing you to talks by someone like Amber Huffman, you get a sense for like how people at that level of education just like talk about the software industry, and you can sort of participate in those conversations. I don't think you need to agree with Amber Huffman, but you should have an opinion on whether you agree with her or not, right? So that kind of thing. I usually try and really push students to think about what software they're using and what licenses it's under. So all of the software used in this course, Python, Tix, GraphViz, Quarto, so the small ones and the big ones, all that stuff's free. I don't think VS Code is open source, right? So I wouldn't traditionally want to use VS Code, but it has some niceties, right? And of course you can use Quarto without using VS Code. And in fact, it seems to maybe work better without VS Code. You can play around with it and see what you think. LaTeX has been around forever, right? So I try to give you access to like a lot of open source things and see how powerful it can be, right? I don't give any big tech companies any money to host any of my stuff, right? And in exchange for that, YouTube can take my videos down, right? If I was self-hosting that, they wouldn't be able to do that. So that's kind of the trade-off we have. Finite automata. So to me, I have always insisted that a finite automata is a 5-tuple. And I always begin at the top, and I don't have to look at this, I can review it. You have your set of finite states.
Sigma.
You got sigma, which is, what is that? We'll quiz you, yeah.
Symbols of
Yep.
states.
Symbols, not of states, of letters.
Letter, oh, yes.
So the finite automata has states and reads letters. I think of it like, I don't know if I told you this example yesterday. When I read a book, like Lord of the Rings is the one I'm thinking of right now, I'm imagining what's happening in the book, but that's not what I'm seeing physically on the page, right? My recollection of where a character is, or what the setting is the state of my mind while I'm reading the input, right? And so it's the difference between sort of what the computer thinks about what it's reading and what it's actually reading. So Q0, or Q, the state, is what it's thinking, and sigma is what it's reading. Okay. And we've got delta.
They have the edges of the edges.
Yep. Absolutely. And then sigma are labels of edges.
Labels of edges.
And then Q is, in fact, they are labels of
States.
something. Yeah, they're the labels of the nodes.
Labels of edges.
Yeah.
And the finished stage.
Yep.
Final stage is
Which is a set.
Acceptance state.
Yeah. Final, finish, accept, true, whatever you want, right? The one state, in a way, because it's the one that returns one. And then there's the initial state, Q naught. And I fixed this on the other slides, but there's still a typo here. That's the wrong Q. That's supposed to be this Q. Okay. There's one other typo on this slide that's just bothering me right now that I just noticed, that there should be a colon after this Q. You see that? This is closure of languages and also finite. So this is the closure of languages of deterministic finite automata under union. And the proof I've duplicated here, actually, and we can see that, this is the NFA proof. So this proof applies to deterministic and non-deterministic finite automata. And that's because its delta has two outputs. So given some Q1 and Q2, some pair of Qs, it returns delta of the first Q with A and delta of the second Q with A. So this is an NFA. And that's why this is so easy. And that's also why we take this union here. The union of the languages should be the union of the ways the languages can be accepted. So it makes sense to have union there instead of intersection or cross product or whatever have you, right? So this is written as the union of the cross products. You'll recall that we showed this another way, and the other way we showed it was simulating both of the machines at the same time and then accepting either one. And then we said, wouldn't this be easier with an NFA? We went and constructed the NFA, and we came back. And here's another cross product right here. But of course, these all have the same sigma, which we are generally regarding as 0, 1. But if we put an A in there, that's fine. Right? Okay. Now, these theorems are in the wrong order because we did NFAs second. But now we're going to demonstrate that NFAs are equivalent to DFAs. You could argue, I guess it doesn't necessarily matter which order you go in, right? Because this proves it for an NFA. And then once you have the NFA, the non-deterministic finite automata, this theorem means that applies to the deterministic finite automata, right? So what do we have here? Ooh, I thought I corrected that. Look at the double L's. So for every machine that is a non-deterministic finite automata, there exists a machine which is a deterministic finite automata that accepts the same language. They don't have the same states, they don't think the same way. It's just, if I give the two of them the same string, they will always come to the same answer. That's all it means. And this wasn't too bad, but this was the introduction of power sets, right? So rather than take the state of sets Q, we have a bit string that measures whether you're in or out of every single state, which means we have potentially 2 to the size of states, possible states. So this Q, if this is of size n, this power set is of size 2 to the n. If I have states A, B, and C, there exist 8 combinations of those states. Right? We never use the case where you are in no states, right? So sigma is unaltered. Delta, we remember, was unaltered. Because the states of the DFA is the power set of the states of the NFA, and because this delta is over the power set of Q, we can use the same delta in the DFA and the NFA. We just use different states. We do have to place Q inside a set, because delta accepts sets of states. And then this mess here, what's this just say? This is just the intersection with the accept state, right? Any set that contains any element of the accept state is accepting. So, and then we get our little box. Did I have a box on the first one? Yeah, see? I got my little proof boxes. That's the best part. You get to write those when you write a good proof. Okay. All right. Concatenation. And probably at this point, after we've done NFA, DFA, and union, it's important to go back and motivate why did we do concatenation. So when I'm thinking of why are we doing concatenation, we're building up to one big result, which is that we want to demonstrate for all regular languages, there exists some deterministic finite automata which models that language, or accepts that language, right? And since the regular languages are produced with union, concatenation, and star exponentiation, right? We're going to have to prove, in theory, right, that maybe there's another way around this proof. We're going to want to show that we can do all of the regular operations over the automata languages. So we're going to do the same thing, right? For any two languages created by automata, there's a third model, a third machine, such that its language is equal to the concatenation. This one wasn't too bad. And I think I actually should have put the picture here, probably instead of the formal statement of the proof. But remember, we just put the two automata next to each other and then drew the lines.
Drew the lines between them, R1 and...
Between, yeah. So R1 and R2 were both accepting states of the first automata. So we had an arrow from every automata that had like the little sigma on it, because nothing. And those went to the second automata. And what did we have drawn here exactly? Exactly what you just said, right? That's the accepting states of the first automata. We require no letter or anything, right? So that's why there's no Q there. And then we go to Q2, and Q2 is the start state of the second automata, right? So we keep these deltas, we add edges between the graphs. That's all. Nothing else, right? This isn't one where we have to add a new start state. We don't need to add new. We just have to use the start state from the first automata and the accepting states from the final automata. Sigma is unaltered. We don't have to do anything fancy with the sets. But this is the special square one because we might have two states with the same name. So we rename the states if they have the same name. And we say, I am state 1 from M1. I am state 2, yeah. And that's mostly, I think, like a notational convenience for us, right? If we think of this in terms of like how an actual computer would work, right? The states don't even have to have names. They can just be. And if they are in a computer, they're going to have different memory locations necessarily, so they're already differentiated. I was a little surprised when I started learning about the deterministic finite automatas that we considered the states to be part of the automata. So my assumption was that they would only exist in delta, and that there's no real reason to put a label on any of the nodes, right? You just say, in delta, I have an arrow from the ith element of the states to the jth element of the states, and it has a label, and they only have indices, right? I think the reason that wasn't thought of is people really liked drawing these graphics out. They were thinking of them as graphs. But I always think of the states as existing in an array. And if they're in an array, none of this stuff matters. Okay. So we've got star closure. After belaboring the point that we didn't need a special start state for anything, we do with star closure. So star closure shouldn't be too bad, right? If we want to have any number of repeats of a finite automata, no problem. We take our accepting states, and we do an arrow back to our start states, and we put the empty string on that arrow, because we don't need to do anything before we can start over again. There's other ways to think of this, of course, if you're stressed out by using the empty string arrows, as I was initially until I convinced myself it was okay. You can just look at every outgoing edge from the start state, and you can make a copy of all of those, and you can attach them to the end state. So if there's a 1 that goes to Q2 out of the start state, you just add a 1 that goes to Q2 out of the accept state, right? And then from there, the only difference you have to do is make sure you're starting in the start state when you're supposed to, right? Nothing too complicated. It's good to convince ourselves of that. My inclination is I'm thinking I'm going to give you an assignment that requires you to prove that, but we'll see. That's not every star, right? And what we saw with the pumping lemma is the usefulness of saying, hey, I can repeat this 0, 1, or 2 times. And right now we can only complete it I don't know. I was going to say natural number, but some people include 0 in that, right? So a positive integer number of times. And star, it was very important that it also includes 0 repeats. So in order to do 0 repeats, we take something that we'd already shown previously, right? The automata that accepts exactly the empty string. And that is an arrow with no label on it, just going into initial start state, going directly into an accept state. I've termed that Q0. It's right here. This is a novel Q that we add to our set of states. So we take Q1 and we add Q0 to it. And so Q0 is an accept state. So we take the union here. Q0 is an accept state, and it accepts before you read anything. And then as soon as you read anything at all, you transmit to the start state and begin reading from there. That make sense? Do you have any questions about that? I have markers today, we can draw it.
You can draw it. I'll be more clear.
I'm going to try and capture this as well. There we go. So I will write, I guess I'll write directly under the screen because that's where that's going to be. Okay. I don't know how other people use whiteboards. This is what I do. I establish the bounding conditions. That marker is terrible. Okay. Much better. Okay. So let's take some example. We'll do an NFA. And one of the example NFAs was null terminated string. Had a self loop labeled 0, 1. And it had a loop to some Q2. And this was labeled 0, because this is an null terminated string. Okay. Q2 is the accept state. Does that make sense?
Yes.
Okay. Now, what we want to show is that we can have an arbitrary number of null terminated strings in a row. This is common. I wrote a C program not 2 weeks ago that had a series of null terminated strings in a row in an array, but the last one was null terminated. And it would have been legal for me to have a string of length 0, because I could have just not had that variable declared, right? So, what is the first thing I claim we do? Well, we add an edge back to Q1, and we put, it's very hard to draw a little sigma, right? I'm just going to draw the empty text. That's what you
Empty state, right?
Yeah. So we'll say empty set. There's nothing in there. I don't know. Is that clear? That's the empty set?
Yeah.
Yeah, okay. Okay, and so this is, I can have an arbitrary number of strings. That's not enough. Come over here. We need to accept, because initially there was an arrow here that I didn't draw. And I didn't draw because I didn't want to erase it, rewrite it, but I have to show it there for example. Okay, so let's unerase that. Oh, I guess I could have just put Q1. So we're going to create a new starting state. And we can't put anything here because that messes up what type of string we have, right? This is our absolute start state coming from nowhere, which means that if we accept right here, we accept the empty string. So we accept the empty string. If we see anything other than the empty string, we're immediately in one of these loops. If the last character we see is a 0, we accept. If the last character we see is 1, we do not accept, unless it's the empty string. Okay, this is one example. We can do this without these kind of sketchy edges, right? And I'm going to show us how we do that. There's two edges coming out of Q1, a 0 edge and a 1 edge. If we think of Q2 as starting the string again, the way Q1 used to, we just have to add those same edges. So Q1 has a 0 edge to Q1, and Q1 has its 1 edge to Q1. We add both of those edges to Q2. Q1 also has an edge labeled 0 that goes to Q2. So we add an edge that goes to Q2. Okay. How do we deal with the empty string problem? Well, we still need this here actually. But as with Q2, we duplicate the Q1 edges. So we have a 0, 1 edge to Q1, the same as this edge. But Q1 also has a 0 edge to Q2. I'm going to go over the top. Can you see that? And so we have a 0 edge from Q0 to Q2. You never need the empty string things. It's just way more annoying to duplicate this edge everywhere, right?
Okay.
We duplicate this edge everywhere. This is a slightly, we'll say, goofy looking case in that there is only one node that is not accepting. So there's more duplication. If I had 30 nodes in here, right, a relatively small percentage of the edges would be duplicated. But this is the example of how you can sort of stitch all of those things together. Does this make sense to you?
Yes.
Should I make you draw one of these? I can give you an example of something you should have to draw. So recall yesterday we had 2 1s in a row was one of ours. Let's see if I remember how to do that. This look right so far? I have to have 2 1s in a row to get to the accept state. If I see a 0, I go back to the initial state. Okay, so this accepts if I have 2 1s in a row. And specifically this case, because the one we started with yesterday had a loop at Q3. This one accepts if your string ends with 2 1s in a row. Okay. Can you convert this from, and I will write the regular language that this represents. We haven't proven we can do that yet, but this is sigma star 1, 1 is this regular language. I can do anything followed by 2 1s. And for us, we have sigma is equal to 0, 1. That'll make sense.
NFA can't have 2 ones in a row, right?
What can't have 2 ones in a row? Sorry?
NFA.
It can.
It can?
Yeah.
Oh.
This could be an MFA, right? This happens to be deterministic. If I give you this string, what sequence of states does this automata pass through to accept this string? There's no state 0.
Sorry?
There's no state 0. What's the first state that passes through?
1. Oh, Q1.
Okay, so we do Q1. You start in Q1. Then I read a 0. And what state do I go to after Q?
Q2.
I go to Q2 from Q1 after
Q1
reading a
to
0.
Q2, yes.
I'm reading a 0. I'm in Q1. What state do I go to?
Q1.
Okay. I'm in Q1.
Reading 1.
Where do I go?
We'll go to Q2.
Okay. And it might be a little bit easier to do like lines like this. I don't know. It's hard for me to write at that angle. Okay.
You got 0 from Q2.
Okay, so I see 0.
Back to Q1.
Back to Q1. Then where do I go? I see a 1.
We have 1 Q2.
Very good.
Then Q3.
And Q3.
Finals.
And that's accept.
Acceptance state.
So this string returns a 1.
Returns 1.
So this bit string maps to that string. Bit string. Or it's not a bit string, it's just a bit, right? You want to do another one?
No, it's fine. I get it.
Okay. Cool. So since you get it, which you were very brave to say, I would like you to modify this automata to be the star version. I believe in you. I'm going to give you some time to think because I need a bathroom break too.
Yes.
But remember, I just did one.
So can I do with the same sequence, 0, 1?
So that's a tough question to answer because the language has to be represented by a DFA, and the star language will contain that string but will also contain other strings. So you could use that string in your example, but that would not constitute a DFA that accepts that language. Does that make sense?
Okay. So I think there won't be any initial state, right?
Yeah, so tell me about the most recent edge you added. So that's a 0 edge from Q3 back to Q1, which makes sense because you're not at the end of a string with only ones at the end of it, right? There's no edges labeled 0 coming out of Q2, and there's no edges labeled 1 coming out of Q3. and I don't know if that's intended or not. So, for example, if I read the string 0, 0, 0, 0, 1, 0, is that rejected?
0, 0?
Any number of zeros, 1, 0.
Yeah, it will reject it because we don't have any coming back over here. There's
Okay.
no string coming back from Q2 to Q1?
Yes.
I think there's a mistake.
And then let me give you an example of when that matters. Consider the string 0, 1, 0, 1, 1. That string ends with 2 1s, so it should be accepted. But it is not accepted by this automata because we see the first 0, we stay in Q1. We see the first 1, we go to Q2. We see a 0, there's no 0 edge, so we reject. But then it's immediately followed by 2 1s, which should accept, right? The reason I ask that is I don't think the 0 edge out of Q3 is necessarily wrong, but I'm not sure what problem it's solving, right? It could be part of a solution if there were some other edges there as well.
Yeah, so it should be so if suppose we are in stage Q2, sorry, stage Q3,
Either works, yeah.
okay, if we get 1,
Okay, if I see a 1,
so will it go back to Q2?
what do you think?
So then I will good. In this case, if we get 1, then it will be back to Q2. If we get 0 at Q2, we get back to Q1.
Okay. What strings does this automata accept?
This string,
What is one string it accepts? Or any number of strings?
I think it was 0, 1, 1.
How does it accept 0, 1, 1?
Can you explain?
So, this as a representation of an automata should represent a function from bit strings to bits.
Okay.
I'm giving, or I think you gave an example of one string, 0, 1, 1. I believe that this automata will return 0 for that string, but you gave it as an example of a string it would accept. I'm willing to be persuaded to your side of the argument if you tell me the sequence of states that results in an acceptance for 0, 1, 1. Does that make sense?
No,
Okay. So if this automata begins reading a string 0, 1, 1,
okay, 0, 1, 1.
yes, it will begin in some initial state. What is that initial state?
Be Q1.
And that will be before it reads the 1. Okay, then it will read, or before it reads the 0, I'm sorry.
Okay, if it is the 0,
Okay, we read the 0, and then what state do we go to?
Q's 1.
Okay, so we're
Now,
still in Q1.
still
Then we read a 1, and what state do we go to?
Q2,
Okay, and then we read a 1, and what state do we go to?
Q3.
Okay, and then we are in Q3. We're at the end of our string, and we reject the string because Q3 is not an accepting state. The language that is accepted by this automata is the empty language.
Empty language.
Because it accepts no strings, because it has no accepting states. Does that make sense?
Yes.
Okay. And that's similar to a proof we showed yesterday that we can always make an automata that accepts the empty language. And the way we do that is by having no accepting states. Does that make sense?
Yes, sir.
Okay. So if you did want this to accept 0, 1, 1, how would you alter the automata to accept 0, 1, 1?
We won't be having back. This should be initial state, right? So I think.
Okay. All right. Does this automata accept every string which ends with 2 1s?
Yes, sir.
Can you show me how it accepts 0, 1, 1, 1?
So if it's in Q3, oh, so I think I found the mistake. Had to be like that.
Okay.
Now in this stage, if we get 0, it will reject the string, right?
Yes. So I'm going to ask you for another example. Does it accept the string 1, 1, 0, 1, 1? That is a string that ends with 2 1s, so it should be accepted, I think, right?
So we are at Q1 now. We go back to Q. We are at the initial stage, right? So
yes, just beginning Q1. We read a 1 from Q1.
Okay, so then it would be go to Q2.
Yep.
Then it will go to Q3. Q2.
Yep.
Gets 1. We'll get to Q3.
Yep.
No, it will not accept it.
Yeah. And it should, right? Because it ends with 2 1s. So how can you modify this so it accepts that string?
We'll pass nothing. No, I did that.
Yeah, because you have to read the 0. You have to have something labeled 0 coming out of Q3, right?
Right, so
Yes. Yeah, that edge was correct the whole time. The problem was it wasn't coming out of an accepting state. So yeah, that as a 0 edge is correct.
okay, now I got it. So we had an extra stage from mirror to process.
Here's something I'd encourage you to look at when you see this. Every state has an outgoing edge for every letter, or every symbol, or every element of sigma. They all have an outgoing 0, they all have an outgoing 1. This is just barely a non-deterministic finite automata. Only Q3 has non-deterministic outgoing edges, and I think you'll never use the one from Q3 to Q2. Because if you keep seeing 1s, you just stay in Q3, because that means you've seen 2 1s in a row. If you want to design this so it must end in exactly 2 1s, 0, 1, 1, then that's a different automata, right? We'd have to start further back, do a series of things, right? Okay. I was going to ask you one more thing. But yeah, it doesn't make sense with this automata. Okay. Do you have any questions about this before you sit down? Do you want to draw
No,
anything?
I got it.
Okay, cool. All right. Good job.
Thank you.
Okay. Let's switch back to display capture. Very good. Okay. So that was motivated by this discussion of star closure. The problem with taking the star closure of this language is accept anything that ends in 2 1s. And if we repeat an arbitrary numbers of strings that can end in 2 1s, it still just ends in 2 1s. So the only way we'd have to alter this one in particular to accept star is add the sort of initial we allow an empty string state, which is not too interesting. All right. We didn't do the GNFA proof. but we did want to introduce GNFAs because we're going to use them for something. This automata right here and all of the automatas we've seen, the edge labels are just the names of letters. Nothing complicated, right? But there's nothing that is preventing us from saying, follow this edge not if you read a single one, but if you read any number of ones, 1 star. And there's equivalently nothing that says, follow this edge if you see an arbitrary number of 0 ones, open parenthesis, 0, 1, close parenthesis, star. That should be fine. And so we're going to say that we can do that. Every operation can be an NFA. So we know we can already build an NFA for all the regular operations. We've shown that. We haven't exactly shown that within an NFA, a node can be replaced with another NFA. But we could argue that, right? And we saw even just with the manipulation of these states, we can add and subtract states and use them for things and various matters, right? So you can always just have all of the outgoing edges from something going into the start state of some other NFA and then coming out of the accept states of that NFA instead of those things going into a node. That's completely fine. So on this basis, we argue that a GNFA is equivalently expressive. There's not some language out there that a GNFA can describe that an NFA can't. There's not a set of bit strings that a GNFA can describe that an NFA can't. Because all of these things are just sets of bit strings, right? And all of this does is returns 1 if it's in the set of bit strings, right? So you can go ahead and work on this sometime if you would like. It's not too bad. It's very similar to the proof in the other direction. This here is the atomicity lemma. And what does this represent? There are 3 atomic regular languages. The empty language, the language which contains no strings. The language which contains 1 string, which is the empty string, which we denote sigma 0. And the language which contains any string of length 1. And these are the letters of sigma. So really, I mean, sigma is already a set. So sigma with the empty set is the first 2 of these, right? And we're going to construct a machine quickly that does each of these, right? M1 accepts a letter. How does it do that? It has 2 states. The states are connected by a single edge. That edge is labeled A. You go from the start state to the accept state when you see an A. The start state is and accepting states are as enumerated. So what does this mean? It's very simple. We have 1 edge. It has the letter on it. That's it. If you see anything other than that letter, you do not accept. If you do see that letter, you do accept. If you see anything after you see that letter, you do not accept, right? Because you've fallen off of your automata. M2. This one accepts the empty string. How does it do that? We have a start state and an end state. That's a typo. That should just say nothing. That's all. And then we have the same thing for accepting an empty language, which is, we don't really care what sigma is, but we have an accept state that is different than the start state, and we have no edges that go to the accept state. So we reject everything. And we can equivalently do this by having a null set here. It doesn't really matter. The only thing you can't have here is you can't have the initial state. Okay. None of those are too bad. I think I'm going to leave myself one note here, just that I think this one is wrong. I think that should be null set. Is Discord loading or not? There it is. Okay. That's probably going to be loading for another 20 minutes. We'll keep going. Okay. So, the atomicity lemmas are perhaps actually more interesting than Theorem 5, because Theorem 5 is just the atomicity lemmas in Theorems 1 through 4. Theorem 1 is union. Theorem 2 is NFA, is equivalent to DFA. Theorem 3 is concatenation. And Theorem 4 is star. This is theorem 5, which says, well, if we can make every atomic regular language out of a DFA, and we can take unions, concatenations, and stars over other regular languages, well, we can do all of the things with a DFA that we can do with a regular language. Therefore, it follows that they are equivalent. I didn't give myself a little box here because I didn't really write a proof. Okay, this one gets a proof. Okay. This here is the base lemma, which is building up to theorem 6. So what is the base lemma doing? Well, let's look at theorem 6 first. So theorem 6 is stating the same thing, but now we are working over grammars, right? So we're going to claim that for all grammars that are of size 2, why is that a grammar? Oh no, sorry, for all GNFAs, I don't know why I'm saying grammars. For all GNFAs that are of size 2, what does size 2 mean? When I say the size of a GNFA, or an NFA, or a DFA, or anything else, any automata, when I say it is of size 2, I'm referring to the number of states. Its number of finite states, so it has 2 states. These two. These are the 2 states. The first one is the start state, and the second one is the only element of the accept, right? So I have a GNFA. The GNFA has some letters. This delta is a little bit different than the other deltas we've seen because this is a GNFA delta, which means that instead of reading a letter and a state and returning as output a state, it reads a letter and a regular language and outputs a state. Otherwise, it is unaltered. Okay, so for all GNFA of size 2, there exists a regular language such that the language of R is equal to the language of the GNFA. How do we do this? Well, we say, this is all by definition, right? That is exactly what we have up here. So then we simply define delta. And how do we define delta? Delta was going to have a start state and an end state, and it was going to read some language. We denote that language R prime, and then we say all we have to do is we set R prime, which we get to specify because we're writing this function. We say R prime is equal to R, and then that means this GNFA of size 2 accepts whatever language this is here, right? The inductive lemma is a little more annoying. This inductive lemma is where we take one state and we pull it out of the GNFA. So we assume the GNFA has more than 2 states. It does not just have a start state and an accept state, there is some intermediate state as well. And so we select that intermediate state, and we notice that there are some number of edges incident on that. There are incoming edges from every other node, there are outgoing edges to every other node, and there is a self loop. It is a simple enough matter to exclude that particular edge. We had this big construction of a new delta, where we take the incoming edges and we concatenate them to the star of the self loop, and we concatenate that to the outgoing edge for each pair of nodes that connects through Q sub 1. So this is the deltas composed that way, and it is otherwise unaltered, right? All we're going to do is we're going to add a bunch of extra stuff to every single edge that's left on the graph. And by that means, we can always take one node out of a GNFA until we get down to 2 nodes. And as soon as we're down to 2 nodes, we have a proof that it represents a regular language. So what this means is that if you have 2, you have a regular language. And if you have more than 2, you can get down to 2 and have a regular language. So they're all modeled by regular languages in some ways. How are you with that? Is that okay? Let's do the pumping lemma. In your own words, what does the pumping lemma do? Do you recall this one? This is a much briefer statement of the proof. This is just to remind us. What problem is the pumping lemma trying to solve? Okay, we have all of these things we can prove that are regular languages. But we also have, for example, the string 0 to the n, 1 to the n. That's not a regular language, but we don't have a way to prove that. So what do? Well, we say, for any regular language that is modeled by a DFA, it can be of some length, some finite length. And so what we do is we take a string that is longer than the number of states. Here's an example. 3 states, 5 letters, right? So I say, okay, I take, and we just think of it as some long string. It just matters that it's longer. So I have this very long string, and necessarily somewhere in this very long string, I repeat a state. In the case of 1, 1, 0, 1, 1, all of the states are repeated, right? You begin at state 1, you go 1, 2, 3, 1, 2, 3. Well, what that means is that at any one of those repeats, we can cut out everything in the middle. So for example, we can look at Q2, and I can say, well, when I first get to Q2, I do 1, 0, 1, and then I'm back in Q2. So I start in Q1, I read a 1, I go to Q2, 1, 0, 1, and then I'm back to Q2. So I can include an arbitrary number of 1, 0, 1s in the middle of my 2 1s. So the string 1, 1 is accepted, the string 1, 1, 0, 1 is accepted. This one's going to be so much easier to write in Python. If Python loads, okay. It's called Python on Windows, not Python 3. Okay. So this is accepted. This is accepted. This is accepted. And in fact, what is accepted? 1 plus 101 times n plus 1 for n in count, but we'll say in range 10, right? All of these are accepted strings, because all of these are going to end with 2 1s. I was so close. This is a string, okay. All of these end in 2 1s. I can write the lambda expression ends in 2 1s, what would we call this? I think this is M1. Lambda of S, and that is let's see, I think that's right. M1 of 1, 1. Is that true? And then this is false? Okay. So what we do is we say, this is our language, and then we say, I'll just look at all of them. We'll say M1 of S for S in L. And all of them have the property we want. I generate the language with the pumping lemma. It must be accepted by M1. I can write no such way of expressing all ones, or exactly n zeros followed by exactly n ones, or exactly n ones followed by exactly n zeros. Because I can't just repeat this thing, 0, 1, a bunch of times, right? I don't have a way to do that. Okay. Now we're going to introduce CFGs. We want to know what the context-free grammars are, because we're going to deal with them in our first sort of sub-lecture today. To lead up to that and to introduce that, I was looking into CFGs a little bit last night because I was trying to figure out who came up with them, was linguists. There's someone named, I'm just going to show you the name. It's Panini, but it has extra characters. Context-free grammar. I have the special characters somewhere. So, Indian scholar, do you know how to say that name? I think there's like something under the N, which I didn't know. I don't know what that character is.
That's called Panini.
Panini? Okay.
Panini.
So Panini, thank you. Panini came up with these things like, what, 2,500 years ago or something? Yeah, like around 2,500 years ago. And those classic MIT people, they formalized it in the 50s, right? But this idea of recursively defining languages has been around forever, right? In grade school, I learned how to diagram sentences, which is one of the ways that English grammar used to be taught. I don't think it's taught that way anymore. And it's a recursively defined grammar, right? So, like, I can say my favorite book is the Iliad. And my favorite book is the Iliad is a complete sentence, right? It has a subject and a predicate. But that's not the sentence I said out loud. I said, I can say my favorite book is the Iliad. So that means that that sentence became the object of the predicate of another sentence, which means that it's recursively defined. Because we can do this an arbitrary number of times. I can say that I can say that I can say any sentence. This is a loop in spoken language, right? So Panini, Panini. I guess Panini was the first person to write this down that anyone's aware of, right? And the interesting thing to me about context-free grammars, right, is that it's so interesting that the mathematicians trying to solve the problem of can I make a function that goes from bit strings to bits came up with the same constructions as the linguists trying to write down how grammar works. And this is especially interesting because the linguists are still scientists, right? But the humans that just started speaking natural languages, they weren't thinking recursively. So there's some naturally recurring cursive thing in the human mind, right? And perhaps in any mind, right? So if there are other things that are intelligent and have language, perhaps they would also speak recursively. My impression from speaking to people, especially in a class, I only speak in a single recursive structure for 60 minutes. I keep saying one subordinate clause after another, and I keep going on, and I never terminate the sentence. So I almost think it is more natural to be infinitely recursive than it is to be speaking individual atomic sentences. And even there, that was one sentence, right? 50 words, very long sentence. Just kept going. So this context-free grammar thing is just pretty interesting. It's pretty novel. Okay. So having talked about context-free grammars for a minute, what are they, right? Well, step one, we have a rule. The rule is the way we generate the grammar. When I think in English, and I only know English, a sentence must have a subject and a predicate. That's it. That's the only rule. There must be there's some action that's taken place, and there's some agent that performs the action. In a Python expression, this is not true. That is a valid Python expression. And to me, that is only a subject. There is no verb here. I do think this is a noun, a verb, and a noun. I take two objects, and one of them performs an action on the other, and we get a result. This is only a verb followed by a noun. But the problem is, that is a noun until I put the parens on it, and then it becomes a verb. these things are quite interesting in Python. So the programming languages are, I think, perhaps even recursively defined in an easier way to think about, because we can always just say everything is an expression, and it is. This is an expression, this is an expression, this is an expression, this is an expression. I don't think this is a legal expression, but I can in fact write it, right? That is two objects that I'm adding them together. They just don't have an add type. This is an expression. And then there's some expressions that are illegal, right? But they're all just expressions. Okay. So in Python, essentially our rule is the type checker. We can't add two things together if one of them is a string and one of them is an integer, or one of them is a function and the other one is a function, right? So we have these rules. And the rules are of the form, we take a variable and we substitute it for something else. And what was the other thing we substitute it for? Some combination of variables and terminals. Terminals are the output strings. There is no graceful way to get Python to print this thing. It prints it as built-in function print. And I could say, but that's printing out a different thing. This is the string print, which happens to be the same name as the function print. So that is actually a different statement. There's no way to print this. Print is a variable. It is not a terminal. And the way to tell is to just type something in, and if it prints out in a different way, this thing, the output, is the terminal.
Okay, it's the terminal.
This is the variable.
Variable.
Okay. And perhaps in that sense, it's even legal to say, oh, actually, 0, 1 plus 1. This is a valid Python expression. It simply evaluates to a type error terminal. A type error is a terminal, right? The code Python didn't crash. Python's still running. It just returned a type error to me, right? So perhaps we say, if you have an s for a string plus an I, which is an int, the terminal value of that is type error. Okay. The variables, those are the things that can't print out. The terminals are the things that can print out. Only variables can appear on the left-hand side of a rule. And the left-hand side is just the arguments of the function. We can think of rules as functions. The starting variable is the topmost symbol. Here's one. This is easier to look at. This is the name of the grammar. This is the topmost symbol. This is a variable. E, T, and F are all variables.
Those are terminals.
These are rules.
All rules.
This is a rule, and what makes it a rule is that we have a variable on the left-hand side. This is recursively defined. That's a variable because it's in a rule, and it's a rule because that's a variable. Okay? There's no easy way to explain that, right? So I have a variable. The rule maps the variable to something else, which is a variable, a terminal, and a variable, or, logical or, another variable. Okay, so this is a rule, this is a rule, this is a rule. 3 rules put together constitute a grammar if all of the rules are well formed and there's at least a non-zero terminal, right? So this is our terminal here. And this is a terminal, and this is a terminal. All of the characters that do not appear on the left-hand side of rules are terminals. That's just the name for something that doesn't appear, right? Terminals and variables together are a set of symbols, but they're not the set of output symbols or the set of input symbols, right? The variables are input symbols and the terminals are output symbols. Here's another grammar. We have a variable that goes to variable, terminal variable, variable, terminal variable, terminal variable, terminal. So this is a terminal. What this means is that an A with 50 parens on each side is a valid member of the language. That shouldn't be surprising to us. Am I close? That's allowed. Why wouldn't it be? It's a very weird thing to write, but it doesn't break anything. You can always add parens, right? And so these two things represent the same language. We introduced this notion of ambiguity. There is more than one way to derive a plus a times a in G3, and there's only a single way to derive it in G2. And that's because this combination of grammars forces us to add parentheses last, then times, then plus, which preserves order of the operations, because that's the reverse order that we would evaluate it in. And this is annoying to me because I think this should be 9. No, that's not what I think should be 9, sorry. I think this should be 9, and it's 7. I guess I also thought that should be 6 instead of 5. Just think you should do the first thing, you know. Okay, here we go. Okay. Now we're going to introduce, and this is sort of the end of review, the notion of a push-down automata. Push-down automatas, basically the same thing as finite automata, either deterministic or not. We are only going to use non-deterministic push-down automata. We would be essentially only using non-deterministic finite automata as well. We just only introduced deterministic finite automata to have a way to explain them, right? There's one difference here. I think that's gamma. Do you know Greek letters at all? I think that's a gamma.
I don't know Greek letters that one.
Yeah.
I thought this is typo or something.
It's the third letter? Wow, okay. I assumed I didn't know because I thought it was later in the alphabet, but okay. So the push-down automata is a finite automata with this thing, and this thing is the stack. It is the data structure of a stack. Are you familiar with the stack data structure? Okay. This is a PDA that has a stack. It can only read off the top of the stack, and it can only write to the top of the stack. But otherwise, it is unremarkable. And this thing is what is going to be the subject of our next lecture. I'm going to need a Cliff Bar. If you want some food, you should go look for it, but my tummy's rumbling. And then we'll start Pushdown Automata in a few minutes. Oh my gosh, it's 6:43 already. Or in this time zone, it's 9:43, right?
9:43.
Yeah.
Is there any vending machine or something?
I don't know. Go. If you need to find food, go find food and come back when you found some. I don't know where you'll look for it, but good luck.
I don't have a key to walk.
The break room was open.
Break room is open?
Yeah. Come back if you need this. I feel like I shouldn't just hand it to you, but I think it's open.
Library.
Okay.
I think it's closed. There's senators.
Yeah, I'll just give you this. Go find something. Take care of yourself. Thank you.
Right back.
Having break? Having break? I'll show you the coffee maker. I'll put some coffee for you.
Thank you.
Of course.
Yeah, cover up to having breakfast.
What? Okay. So, one cup of coffee? Yeah. What? So, go ahead.
Thank you so much.
Tomorrow you have class at 2 as well, right?
Yes.
Okay.
Okay.
Where are you leaving tomorrow?
My flight's at 3:30, so I'll have to wait. Oh, we should talk while you're here. I was going to give you a ride to the airport at noon. Is that okay, or did you want to try and sort something else out?
What time's your flight?
My flight is at 10.
Yeah, so that'd be a long time to get here.
But I have to check out to the hotel, so I'll probably.
Oh, yeah.
The airport has nothing to do with it.
Okay.
No
Your
store, no.
word's not mine.
Nothing to do with rest. Guarantee you that.
Yeah.
All right. See ya.
This is good. I was, when I teach the night classes, I walk to a little cafe. We do a break like every hour and a half. I walk to a cafe and I have to get one of these. It's the only way I can talk for 4 hours. I didn't know where to go yesterday. One of these had an error in it. I'm trying to remember where it was. Oh well. You know, you work so hard on these things and then they're just like riddled with errors because it's so technical. And then I wouldn't care, but like when I'm writing an email, if there's a typo, everyone still knows what I mean. But if you get like one subscript wrong in a pushdown automata, it's a completely different automata, right? The information density is so much higher. Okay, so I save that. I'll save my work, and then we'll close this. Okay. All right. So we've been talking about automata for a while, and we're going to introduce a few new things all right now, all in support of the pushdown automata. So I have been articulating to you a deterministic or other finite automata is a 5-tuple. A pushdown is a 6-tuple, only has one difference. And we have also, I have articulated that we can think of them as graphs. So either a graph or a 5-tuple, these things are equivalent, right? As we elevate our thinking to sort of the level of a Turing machine, and this is the intermediate step between finite automatas and the computer itself, right? It's helpful to start thinking of this as a different way, where we don't really think about the individual states. We just understand that the states are in there. Now, for you, this is going to be particularly difficult because usually you'll have had 3 weeks, including 3 homework assignments, on dealing with graphs and tuples. We're going to jump right into schematic, and then we're going to go back and clean it up with homework later. So just be aware of that. Usually at this stage in the course, what's happening is we start abstracting things that we already understand completely. You saw them yesterday for the first time. So this could feel a little bit like a black box where it's like it doesn't make sense what's going on in that thing to you. So just be aware of that and go back and figure it out later. Let me show you the schematic view so I know what I'm talking about. All right. We're going to start to use this term called the finite control. And what does the finite control represent? Well, it represents, I don't necessarily want to say the internal state of the finite automata. To me, it represents the memory of the computer, right? But it's whatever state an automata is in, finite, pushdown, or Turing. And we just are going to just like put a box on the screen and say, this has some state right now. We're not going to say what state it is. We're not going to say how we figured out the state. We're just going to say this has some state right now. And the states are altered by reading symbols the same way we've been reading symbols with finite automata, right? So it's all the same thing, but we're just going to start using the term finite control instead of saying it is in state Q0, it progresses to state Q1, it progresses to state Q2, and then it loops back to Q1. This is easier to think about when we think about just the finite automata. Why? Well, in a finite automata, you only have one state to worry about. The pushdown automata has more stuff than that. The finite control of a pushdown automata also includes the entire stack, which is potentially, it's unbounded memory. It's an arbitrarily large amount of memory. I don't think we've introduced this or talked about this, but the pushdown automata can handle infinite length languages, no problem. We're not going to use them for that, but they can, right? And so we're just going to put all of this in a box. Why box? Very simple. I used circles for states. I'm going to use a box for the finite control, just so it doesn't look the same. That's all the thinking that goes into that. And we're also going to introduce an additional sort of piece of terminology, and this is literally exactly from Alan Turing himself. He was the one that came up with this, and we just all did it because it was an easy way to describe it. We're going to now think of the string we're reading being on a tape. And why are we going to say tape? Well, we need some word for it, and there isn't a great word for it. And the tape is essentially something that is potentially infinite in length in both directions. We can think of 1, 1, 0, 1, 1 as being a series of characters that occurs on some tape, and then past the 1 1s in each direction, there's just nothing on the tape, it's blank. But we could put more symbols on the tape if we wanted to. We could put up to an infinite number of symbols on a tape. So we're going to start calling, instead of the input string, we are now going to refer to the tape. The reason we're going to start calling it the tape is Turing machines can read and write from the tape, which means they can edit their input strings. The finite automata can't do that, they just return 0 or 1, right? The pushdown automata can't do that either. But because we have the stack now, we're going to use a different term to refer to the input letters as the stack letters. So there's going to be some internal storage and memory inside the computer, and then separately there's going to be something that it's reading on a tape. My understanding is that even now there are trace amounts of computer data stored on tapes. I believe things like government records are stored on tapes. So I do want to motivate you, and I don't know what computers you've worked with, right? But right when I was growing up, there were still tapes around that you would plug into an early computer, and you would write onto a tape and read onto a tape. Tapes are a magnetic storage medium, right? So it's a magnetically active material somehow. Not very good at chemistry. That could be physics. I don't even know if it's chemistry or physics. It's one of the physical sciences. I get in so much trouble with my partner because she starts describing what she's doing to me, and I'm like, isn't that physics? And she's like, no, that one's chemistry. I was like, dang it, didn't even get that one right. But, you know, neither here nor there to me.
It looks physics to me.
Right, and in my defense, right, she's a physical chemist that works with these things called quantum dots. And I've never heard of quantum chemistry, but I've heard of quantum physics, right? So I hear quantum, and I'm like, oh, the next word that's coming after that is either physics or computer, right? And no, she says dots. And I was like, well, what's the dots? She's like, it's a chemical. And I'm like, oh, no. Like, so anyways, quantum dots they're cool, whatever they are. Some kind of nanomaterial, right? I never could do a real science, right? Like, I'm so good with the computer where you just type things in and you hope it works, right?
Yes.
She has to like do vials and all this. So anyways, back when computer science was hard, they had to store things on tape, and actual real existing physicists or chemists had to make those tapes. But this is really not that far off. It is hard for me to determine from my position in academia exactly what is going on at the only 3 places in the United States that matter, which is Amazon, Microsoft, and Google, which control probably 70% of the world's computing power, though maybe not as of a few weeks ago, right? DeepSeek coming out suggests the Chinese have considerably more computing power than we thought, and good for them. And I don't know how your home country is doing, but at some point India is going to have the most powerful computers in the world. I just don't know what year that's going to happen, right? So that'll all be very exciting. But for now, there's 3 computer companies, and their names are Amazon, Microsoft, and Google, right? They have some kind of very, I'm going to say, exotic computer hardware that doesn't necessarily work the intuitive way we think of it from having been able to work with our physical devices. But one of the things they have is enormous banks of solid-state drives. I have 1 solid-state hard drive. And with my 1 solid-state hard drive, what it's really good at is I say, go to this file location and read until I tell you to stop. And so it is very good at reading a movie off of my hard drive, or it is very good at reading an operating system off of my hard drive. And in fact, I can show you that I can just boot another operating system right now by typing WSL, and it will boot the Linux operating system. That is 20 gigabytes of data, and it's just going to read all of it in a single block read, as if it's reading from a physical tape, right? So even though the solid-state hard drive, or that's not a solid-state hard drive, the solid-state drive is just a big bank of transistors, it feels a lot like a tape even now. And one of the early results of sort of cloud computing optimization, right, is initially when the solid state drives, everyone came out, everyone said, these are random access memory, we're going to treat them like random access memory. And in fact, they're not, because the poor humans that have to construct these things still have to connect wires to transistors somehow. And basically every human ever is going to do that in what looks an awful lot like an array. And something that looks an awful lot like array is something that you read linearly. And so even the solid state hard drives that are in theory random access memory have higher performance when you read the bit that you wrote just after the bit you wrote before it. So everything is essentially sequential. I've read a number of blog posts and I haven't found good results on them. That cloud computing algorithms, which are very confusing and complicated and frequently not written down and have to be studied in abstract because they're proprietary to the three big companies. They seem to be optimized around reading large amounts of data from a solid state drive in one read. And that is exactly what the Pushdown Automata were engineered to do 50 years ago by Chomsky and 2,500 years ago by Panini. Panini? Yeah, okay, I'm gonna get it. That character under the N, I don't know what that's called, but I have no idea how to say that.
Under N, it's in the middle, Panini,
Ni.
It sounds like, your twist your tongue.
Ni. I'll practice. Okay.
So different letter from.
That's cool. I don't know. I always try and, I was complaining to you yesterday that everything's named after the Europeans, and I'm like, I'm pretty sure the Europeans didn't invent having languages. And you look and it's like, oh, yep, that's an Indian scholar, right? I get myself in trouble from time to time because a lot of the cryptography, I believe it was discovered by essentially Muslim scholars during the Islamic Golden Age. And at various points in time in this country, people assume you're only talking about Muslim scholars if you have some political axe to grind with the current government. And it's like, no, I looked up who invented cryptography, and it was some guy in Egypt 600 years ago, and that's not my fault. And so I should do a better job knowing where all this stuff comes from. So the first recorded use of binary was also somewhere in Asia, right? And the Europeans, of course, want to take credit for that with Turing, but that was several thousand years after other cultures had been using binary, right? And like good for Turing, right? But like he didn't invent that idea, right? He was just the first white person to do it. Okay, so I said that out loud, and hopefully you were thinking about what you thought it looked like. Here's a graphic. This is just from Wikipedia. This is one of the few external graphics I use that I didn't make myself. And the reason I wanted to show this to you is I wanted you to see how other people are visualizing this thing, right? We have a finite control. I'm not the one that named this thing delta, right? Everyone calls this thing delta. That's a delta right there. Why do we put delta there? Well, delta, when I've talked about it, right, that's very close to the entire computational strength of the machine. It contains necessarily all the names of the states and all of the names of the transition labels, right? Okay. So we have our finite control, we abstract it as a box, we say delta lives inside the box, and all delta is going to do is it's going to be reading off of this input tape. A is our first letter. Here's the infinite tape on both sides of the string we're currently reading. So imagine an infinite number of blank spaces on both sides of 11011. Okay? We are looking at the Pushdown Automata is always looking at exactly one character. It does not know what is on either side of the character. It can only read one character at a time. Let me motivate this again by a physical example. In between tapes and solid-state drives were hard disk drives. My first job in undergrad was I worked as a firmware engineer for Seagate Technologies shortly before they were borderline run out of business by Samsung for making solid-state drives. It was a very interesting time. They essentially went from being a profitable to non-viable company while I was there during my internship. It was one of the most rapid technology changes I've ever seen in my life. They had actual physical Samsung drives there that they were testing. They said, we're still so much better than this. But they had the commercially available Samsung drives they were comparing to their experimentals. And the Samsung experimentals were already better than their best experimentals, right? So they never made it to market in time to be competitive. Seagate still makes outstanding hard disk drives that store things like 100 terabytes, but no one has 100 terabytes of data to store except Google, and Google can afford Samsung drives, right? So, poor Seagate, they were a big part of the local economy growing up, and I have a lot of respect for the people that work there. But at Seagate, their innovation was they had a bunch of physicists. And the physicists were really good at making very, very small magnets. And these very, very small magnets read a rotating magnet that looks a lot like a CD or a DVD or a vinyl player or anything like this. So they were some of the first people that moved things off of tapes, which are round and straight. And they said, I'm going to put this on a rotating platter, right? But one of the really big performance improvements they got is they were trying to store a bit in a smaller and smaller amount of magnets. So there was just a magnet that's either positively or negatively charged. And they had a head that rotated around and was on a servo motor going back and forth over the platter, and then the platter rotated. They found out that they didn't need to have two sensors, because initially they had a read, which was a magnet that turned on and off and set the value of something, and a write, which measures the magnetic value. They said, well, actually, we just need one magnet, and we put a different current through it to determine whether it's reading or writing. That is the notion of a finite control. It is reading and writing at the same time. It cannot do both, but it only has one exactly fixed position anywhere on the tape. To me, this exactly maps how actual existing physical hard drives had to be made by physicists who didn't learn automata theory. They just had to do something that made sense. This is the naturally occurring way to read memory, is my view. And this is not still the case with solid-state drives, where you just push current through a series of transistors and something comes out the other end, right? But both the tapes and the hard disk drives, which were used for 40 years, all had a head, they call it, which was a reader-writer sensor. And it looks at a specific bit, and it reads one bit at a time. And it just reads 1 billion of them a second, right? That's probably not true. It probably reads 1 million of them a second. But it reads very fast, though not fast compared to solid-state drives. Okay, so, oh, is there anything else I want to say? Ah, the stack, yes. You know what the stack data structure is. Stacks are very easy to model. Really, I can't do that? I was pretty sure I could do that. Huh. Maybe I don't know how stacks work. Okay. Do you know how stacks work in Python? No one actually uses stacks in practice. I was sure I could push onto.
No, I think.
Because you can pop off of lists. Let's see, if I do this. That's allowed, right? I've done it before. It's probably even on the next slide.
It's append. You can.
Oh, it's append. Thank you. All right. Okay. So we're going to do. We're going to say stack equals nothing. We're going to stack dot.
Append.
Ooh, wait. I'm losing performance. Okay. That's pretty fast. Stack dot append. We'll do 1 1 0 1. 1 1 0 1. I'm going to do a 0 here now because I don't want it to be the same backwards and forwards.
Okay.
Okay, so let's look at our stack. Okay, and then we can pop things off the stack. What's the first thing we pop off the stack? The last thing we put on there. We have to be careful here because Python pop is actually implementing a queue. And I'm going to demonstrate that. If I stack pop naively, this is going to take the first thing off of the stack, which means it's not a stack. It means it's a queue. It's first in, first out. Ooh, no, it works. Okay, cool. And then we get a 1, then we get a 0, then we get a 1, then we get a 1. Okay, we've done it. Yes, we have a stack. Okay. Right? We put a 0 on last.
The backward, right?
Yep. And then we pop off the 0. I thought I was going to have to say, I thought what I would have to do is say stack pop -1, which also works. But we can contrast that with, this isn't a Python class, so we don't really need to show all of this, but there you are. Stack pop 0, this is going to take the initial element, right? 1 1 0 1 1, and that's a queue. Okay, so you know what a stack is. You were able to implement one quickly. Good job finding append. Okay, so we take our finite automata and we say, by the power vested in me by Turing machines, on which we're running all of this stuff, you may now use the notion of a stack. And with the power of a stack, you are now equivalently powerful to a context-free grammar, and that is not easy to prove, but we are aware of it, and we're going to continue. Okay, finite control. Finite control of an FA is just the internal states. Finite control of a pushdown automata is the finite state it is in and its current stack memory.
Stack memory.
Really, these things are both memory, right? In 1950, they didn't know we were just going to write everything to solid-state drives, right? They assumed we'd have different types of memory. Good for them, right? We don't need that abstraction anymore. Now we have random access memory, which is just like a Turing machine. Okay, there's an input or a tape, pushdown automata. I hand you a tape. The tape has a series of zeros and ones on it, just like a cassette tape, just like a solid-state drive, just like a hard disk drive, just like a book, which has a series of characters that could be expressed in binary, right? Input, exact same thing. We are only allowing our automata to read forward. Pushdown automata can only read forward. Finite automata can only read forward. The Turing machine is going to have the ability to read backwards. We will get there. We'll leave it on the slide for a second. The tape and the stack don't necessarily have the same letters on them. What does that mean? It makes enough sense to think that this is actually the first introduction with context-free grammars of different types of things. So the context-free grammars have variables and terminals. Variables live on the stack. Terminals live on the tape. That's the difference to me. A variable is not something I tell anyone about. I'm using it internally for my computation. In the very olden days, perhaps this is still done actually, when I took my first math classes, students would ask for scratch paper to write their computations on, right? Those computations are on the stack. Those are variables. I don't turn those into the teacher, right? I do my work, I write down my answer, and those are the terminals, and I turn those in. And the stack disappears, it goes away. It's not considered by my teacher, right? So that's one way to think of this. This is just sort of an internal language I use for work. I was talking to one student. We recruited a statistician into one of our master's programs, and we don't have an undergraduate stat major, so it's actually very nice to have statisticians in the class because they can check our work, right? Be like, oh, that's how that's taught at another university, I didn't realize. So we were talking about discrete random variables or something, you know, just some topic that's of interest to statisticians, right? And I was like, oh, can you show me your notes from undergrad on this topic? And he's like, oh, I can write them up for you. And I was like, oh, you can just show me what you have. He's like, no, you won't be able to understand that. That's in my chicken scratch, right? It's in variables. Only this student can understand that, right? Only the pushdown automata can understand the variables. Only your undergraduate stat major can understand the chicken scratch on statistics. It is the terminals, which is the LaTeX document that he actually turns in, that I can understand, right? So it's not unusual for us to have this notion of internal representation, right? For example, right now, this is all HTML. We're not looking at HTML elements, yes, right? Okay. We're looking at the terminals, right? Terminals. They're represented differently. This is a bold T. There is no notion of a bold T in HTML. You have to do a strong type or an emph type or a font weight bold, and then you just write a regular weight T inside of it, right? Bold T is a terminal. Capital T is a variable. It's also a terminal. There's a lowercase non-bold T, right? Okay. Stack. It's the memory of the automata. One of the examples of a finite automata we did is I said, hey, I think this string has an equal number of zeros and ones. Can you check it for me? With a finite automata, we proved we couldn't with the pumping lemma. We said there's no way, you can't do it. And the reason for that is I can give you a string of length 1 billion, and then you need a billion internal states to count up how many more ones you've seen than zeros, and then you have to count back down. And your accepting state is when you have the same number of zeros and ones, right? So you sort of have to say, sort of how, like, we count, oh, we've had 2 ones in a row. Then you just count back the other way with zeros. But the problem is, if you make your finite state machine that's able to read strings of length a billion, I say, I have a string of length 1,000,000,002. Can you tell if this has the same numbers of zeros and ones? And you can't. And that's essentially the pumping lemma. That's why it's unsolvable. I can always just take a string longer than your number of finite states, and then you can't check that. All of a sudden, no problem. This stack is uncapped. I can put 1,000,002,002 characters on this stack even if I have 1 internal state, right? And so what this means is that now, because the pushdown automata has memory, it can instantly and trivially recognize the same number of zeros and ones. And what's it do? It's not too complicated. Every time it sees a 0, it puts it on the stack. Every time it sees a 1, it takes a 0 off the stack and puts a 1 on the stack, and so it just has a counter of how many more zeros or ones it's seen. And then when it hits the end of the string, it looks at its stack, and if there's nothing there, it accepts. And if there's anything there, there was more zeros or more ones. Not complicated at all. We've talked about the head a million times. Do you do vinyl at all? There's there's people call them records. There's these old big, like, they're for music, and they have like songs on them, and you like put a head on it. Yeah, I don't even know what they're called. I call it vinyl. Some people call it record players.
Cassettes, I think.
Yeah. That's the best. I'm going to type in vinyl player, and we're going to see what pops up. Right, this thing has a visible head on it. Okay, this is the easiest one. Oh, turntable, perhaps. Maybe that's what I should say. Yeah. Right over there. That's the head. That's what a head looks like to me, right? I always visualize this type of head, like I've seen on turntables. Turntables, goodness me. Okay. Right. The stack. Okay, you know what a stack is.
It's like the old gramophone.
Yes. Yes, exactly. Yeah. Yeah, how's that even? G-R-A-M-O-P-H-O? Yeah.
Gramophone.
Did you, how many of those have you seen? I think I've seen like one of them in a museum or something. Were they around when you were growing up or anything? You know what they are.
One of my friend's house.
Yeah, someone had one.
Someone had one, and
Yeah.
I never used it, or I never listened music to over there, but I saw it.
Yeah.
Sitting over there in the thing.
It's so interesting to me that like we'll never see stuff like that again, right? The computers are too fast now. Everything will be done digitally, right?
Now,
Well, you were talking about driving. You're like, oh, I've never driven a car with gears. And it's like imagine telling that to a mechanical engineer 10 years ago. They'd be like, how do you make a car without gears? It's like, oh, you have servo motors and you have a computer, right? But like all of these abstractions, it would have been very hard for people to come up with them if they lived in the world we live in now, where everything is you push a button and then it works, right? So all of the technologies that were around 70 years ago, like a gramophone, contain elements of the things we use to describe this. So we're like, oh, we have a tape with a head, and it's like, well, that was a cassette player when I was growing up, right? I could see the actual components, right? And then, you know, I talked to like a 19-year-old in one of my undergraduate classes, and they're like, what's a cassette player? I'm like, this might be hard for you to understand because you've never seen anything in your life that isn't, you just push a button and the screen works, right?
have you seen one of those cassette pairs, like cassettes with circle in between them, and there's a tape?
That's exactly what I'm thinking of, yeah.
Yeah, that's.
I'm thinking of these ones. I think if I type in cassette tape, ooh, come on, load. You can't actually see anything, but this thing,
Yeah, exactly, yeah, that's it.
And then VHS is just bigger but looks the same. And actually, like, those are the old analog formats where it's not actually stored in bits. Those are an infinite precision storage medium, right? It's this, the limit of the storage is how good the physics and chemistry are, right? My partner's also a little bit into photographer and shoots digitally, right? But there's all these pictures that are 150 years old that are higher resolution than our modern cameras because it's just physical film. It's infinite precision. The precision of it is the quality of the light passing through the aperture of the lens, right, which you can't surpass. And it's so interesting, something like VHS, right? You could, in theory, have like extremely clean lines on that because you have no pixels. It's just, or you do have pixels, but they're chemicals, right? It's the actual pigments. Right. Our restriction, and this is very, very important. It can only write certain symbols, but it can have any finite number of symbols, right? So you can pack a lot of information in here. This is sort of getting to the beginning of teasing the later innovation, which they didn't know this at the time, I don't think, of data structures, where it's like, the symbol I write is a JSON file that is 1 terabyte in size. And it's like, well, yeah, that is technically one thing, right? And I have some JSON running in the back end here. And you can only read the most recent symbol. So this is going to matter a little bit. But a lot of times when I talk to students about this, they're like, I see if there is an A anywhere in the stack. And it's like, you cannot do that at all, right? You can only see the most recent thing you wrote to the stack. As soon as you can see the whole stack, what you're talking about is a Turing machine. And those are much, much harder to build, right? They did not have Turing machines when they started doing this, right? Think the stack abstract data structure, you know what that is. Here we have. We spent all of that time finding append and pop, and it's right here. So, okay. Okay. Think of an NFA. The only difference is that it can look at symbols. Oh, yes, here's another thing. So I think the stack data type in one of the big programming languages, and it probably can't be Python, has a peek operation. And the peek operation is you look at the symbol on the top of the stack, but you don't take it off. And that's not allowed here. That's sort of a modern stack thing. So if you haven't heard of peek, don't worry about it. Have you heard of peek?
I think it's in Java.
I bet it's Java. So we don't have peek, right? So just be aware of that. And because one of the reasons is, since the whole point of this is to understand things and how complicated they are, if you start using like a modern Java technology, it's like that's kind of defeating the purpose, right? So that's the only reason to have that distinction. So if you need to peek something, you have to write and read and somehow, right? Okay. Here's the exercise. Okay. I'm going to ask you. Do you have these slides up? Are you looking at my slides right now?
Yes.
Okay. The answer is on the next slide. Try and figure this out yourself. If you get stuck, look at the answer. I've expressed my answer using the def keyword to write functions. Even if you just translate it to lambda expressions, that will still constitute a contribution. I'm going to take a walk again, because I didn't make it all the way through yesterday, so I'm taking more breaks today. So give this a good shot. And the way we're going to do this, oh goodness. Okay. I'm going to give us a 10-minute timer and just think about this for 10 minutes, and then we'll be back. Oh, my computer is struggling. Okay. I need to close as many windows as possible. Okay. I'm actually going to have to restart my computer in the hopes that it cools down a little bit. So I don't know if this will be exactly 10 minutes. I'm going to grab my watch.